this video, we're going to take a look at how NTP sets the time on a client PC. Firstly, we'll have a look at the basic protocol exchange. Then we'll have a look at some actual example packets, and finally we'll look at how that packet data is used to calculate the time offset and set the time on your system clock. So before we get going, I'll give you an overview of the hardware setup that we've got today. So we've got a Windows 11 PC, and that is running the basic built-in Windows time service as our NTP client. We've got a Sync Defender network time server as our NTP server, and this is locked to GPS. And these two devices are connected together by the Ethernet switch that I have here. Links to all of these are in the description box below. Okay, so that's the setup covered. Let's move on to the basic protocol exchange. Our setup today uses the standard NTP client server model, and this is how most NTP installations operate. The NTP client sends a message to the server requesting the time. The server then replies directly to the client with timing information. The packet format is the same for client and server messages. Messages are sent using the user datagram protocol, but in this video we are just looking at the actual NTP packet data contained within the UDP payload data. The packet data can be split into 4 different types. We've got info data that tells us fixed information about the device sending the packet, status data that changes depending on the device status, the actual timestamp data, and finally the optional extension fields. There are 5 info data fields. The version tells us the NTP version the client is using. This basically specifies the meaning of all the data fields in the packet. The server will reply using the same version. The mode tells us the association mode being used. To put this another way, this tells us the relationship between the device sending the request and the device responding to the request. In a typical client-server interaction, such as our setup today, the client will use mode 3 and the server will reply with mode 4. The precision tells us the precision of the system clock. The route delay is a measure of the total round-trip time between an NTP server and its reference source, and the route dispersion is an estimate of the timestamp error. These last 3 fields are useful in larger NTP setups as they can help an NTP client to choose between multiple NTP servers. Something to note here is that these 3 fields could actually change, but they don't normally with a STRATUM 1 server. Looking next at the status data fields, we've got the leap indicator, the stratum, the pole interval and the reference ID. The reference ID is a 4-character code that tells us what the server is synchronized to. The pole field represents the interval between NTP requests. This is commonly set to a value of 6, which represents 64 seconds, although some NTP client implementations use a longer pole interval. Also note that this value can increase as an NTP client becomes more stable. The stratum tells us the distance from the reference clock. The leap indicator tells us whether the time has ever been set and also warns of an impending leap second. The stratum and the leap indicator are both really important fields that the NTP client uses to decide whether to trust the time from the server. We've done separate videos on both of these fields and the links are in the description below. There are 4 unique 64-bit timestamp fields. The reference timestamp tells us when the system clock was last set. The origin timestamp tells us what time the client sent its request. The receive timestamp tells us what time the server received the client request. And the transmit timestamp tells us what time the packet was sent. Something worth keeping in mind here though is that if you're looking at an NTP client request packet, some of these fields may be blank. This depends on the client implementation and status. Also note that in a client request message, the transmit timestamp is the system time of the client device at the point the client request was sent. The server copies this timestamp and uses it as the origin timestamp in its reply. The extension fields are optional, and if they are used, they're usually providing authentication. Let us know in the comments if you'd like us to cover this in a future video. Okay, so that's the basic protocol covered. Let's move on and look at some actual example packets. So if I force the Windows time service to resync, this will send the NTP request to the server. If we now jump across to Wireshark, we can see the two NTP packets. The top one is the request from the client, and the bottom one is the reply from the server. Looking at the NTP client request packet data, we can see the Ethernet frame data. Inside this, we've got the IPv4 header. Inside that, we've got the UDP header with the NTP source and destination port specified, and then the actual NTP packet data. This is what we're interested in. There are a few points of interest here. The Windows Time Service has sent the NTP client request using NTP version 3. This is an older version, but works perfectly fine. The polling interval is set to 10, which works out to 1024 seconds. The origin and receive timestamps are both set to all zeros. Wireshark displays this as null. The thing we really care about in this packet is the transmit timestamp. This is set to 13:51:58. Let's make a note of this for use later. If we now open the NTP server reply, we can again see the Ethernet frame data. Inside this, we've got the IPv4 header. Inside that, we've got the UDP header with the port set to 123, and then the actual NTP packet data. Looking at the points of interest in the server data, we can see the leap indicator is set to no warning. So we know the time has been set on the server and there is no leap second warning. The NTP version is again set to NTP version 3 to match the client request. And the association mode is set to 4, as this is a server reply to a client request. The stratum is set to 1, as our server is a primary stratum 1 server and the server is synchronized. The polling interval is set to 1024 seconds to match the client request, and the reference ID is set to GPS as our NTP server is using GPS as its reference. Now we come to the timestamps. The reference timestamp shows us the server was last synchronized on the second edge preceding the receive timestamp. This makes sense as the server updates its time internally on the second edge. If we look at the origin timestamp, this is identical to the transmit timestamp from the NTP client request packet that we noted down earlier. We can also see the server has also added the receive and transmit timestamps. These indicate the server system time when it received the NTP client request and transmitted the NTP server reply. That's our example packet data analysed. Now let's have a look at how that packet data is used to calculate the offset and adjust the system clock on our client PC. So, there are 3 steps to this process. The first thing the NTP client does after receiving the reply from the server is to check the data is valid. So as a minimum, it looks at the stratum value and leap indicator. It might also look at some of the other values, but this depends on the implementation. If we go back to our packet data, we can see there are no warnings. The server is locked to GPS and is set to stratum 1. So the client knows that the timestamp data is valid. Next, the NTP client software calculates the offset between the client PC clock and the NTP server. It does this using the formula shown on screen. Don't worry if you think this looks complicated, it's actually quite straightforward, but really clever. T1, T2 and T3 are the origin, receive and transmit timestamps from the server reply message we looked at earlier. T4 is a new timestamp created by the NTP client marking the point it receives the reply from the server. If we just look at the first grouping for now, T2 minus T1, this is the time difference between when the server received the request and when the client sent it. If the server and client clocks were perfectly synchronized, this would just be the network delay. But since the client's clock might be fast or slow, this measurement includes both the network delay and the clock offset. Looking at the second grouping now, T3 minus T4, this is the time difference between when the server sent its reply and when the client received it. Again, this value includes both the network delay and the clock offset. However, because we are looking at the return packet travelling in the other direction, the network delay part of this value is inverted. So when we add the 2 groupings together, the network delays cancel out and we are just left with 2 times the clock offset. Dividing this by 2 gives just the clock offset. Of course, this assumes that the delay across the network is the same in both directions. For most networks, this is a fair assumption though. In the final step, the NTP client software looks at the offset and decides what action to take. This action varies depending on the client software, the size of the offset, and how many samples the client is working with. Some basic implementations just hard sync the clock, assuming the offset is below a set limit. This causes a time jump though, so it's not ideal. More advanced implementations make small adjustments to the speed of the system clock, trimming out the offset over a period of time. This is a much more elegant solution that avoids time discontinuities. If it would be of interest, maybe we could do a series of videos of how different NTP clients implement this. Let us know in the comments below if you'd like to see this. In this video, we've had a look at the NTP packet format and how this can be used to set the time on a client PC. One small part of the NTP packet format that we've discussed briefly is actually really critical for an NTP client to decide whether it's going to trust the time coming from an NTP server. If you'd like to learn more about this and how NTP clients prevent timing loops, you might like to watch our video on NTP STRATUM values. The link is coming up on screen now.